quickly going over what we went over in class today. Of course, if you weren't in class, you missed the entire exchange of information. But following along with responses of various students to questions posed in the process, we developed this diagram to show how we calculate, to summarize and to represent how we calculate the acceleration in a situation like this. Okay, so we give the car a poke, we figure out how long it takes, how far it goes. What do we know about that motion? We don't know the initial velocity. We didn't measure the initial velocity. We do know the final velocity came to rest. And I had some confusion on that. I was using an initial velocity of 0. Of course, that last ramp is no excuse, but that last ramp was on a slope where the initial velocity was 0, and we calculated an average velocity and the final velocity. Okay, anyhow. Initial velocity for this example was unknown. Final velocity was 0. The distance, the displacement, delta S, we knew, and the delta T, we knew, at least to the extent that we can do a steady 8 or 10 count. And of course, everybody's 8 or 10 count will vary from that of somebody else. We just count that at the pace at which we're comfortable, and we'll have a fairly consistent pace. Okay, anyhow, so having observed delta S, delta T, and VF, how do we determine the remainder of these quantities? Now we have the quantities V naught, VF, V bar, delta V, delta S, and did I say delta S? Delta V, delta S, delta T, and A. Okay, 7 quantities here in terms of which we reason out rather than using an equation to determine the motion of the object on the interval. Of course, if we know VF, delta S, and delta T, we can pull out equations. And those equations are great. It's a very wonderful thing when somebody can use the equations in a consistent and useful manner, okay? Consistent and valid manner to solve difficult problems. But there's another dimension to understanding a situation, and just because you can use the equations to solve a problem doesn't mean that you know how to solve the problem, that you really understand the entire situation. Now, if you use the equations to solve the problem and then come up with a valid interpretation, you're going to be a lot closer to complete understanding of the system. But here's another approach that also leads us to a deeper understanding, especially you can't do without the equations, but you can do a lot of things without the equations, and they inform you of the situation. They give you deeper understanding, deeper information, and make it possible for you to solve problems that you might not otherwise be able to solve. Whether you're using this or not, the understanding that comes from this kind of direct reasoning can lead to real benefits. Okay, so if you know the final velocity, delta S and delta T, the question I posed, and of course this stuff wasn't written here, the question I posed is, what can you determine? What can you determine by simple reasoning from the definitions? And the answer to that is, well, you've got delta S and delta T, and by the definition of average velocity, which is the average rate of change of position with respect to clock time, and that by the definition of an average rate being equal to the change in position divided by the change in clock time, you can divide delta S by delta T to get the average velocity. Now that's something you know to do without even having to resort to the definition, but you want to go back to the definition to put this on a rigorous basis. So you get the average velocity. Now you know VF, delta S, delta T, and the average velocity. What can you do? Well, if you know the average velocity and VF, you know, now I've drawn the picture here where V naught is 0. For the example I just showed you, VF was 0, and the graph would have looked something like this. But you've seen both kinds of graphs. I'm just reminding you something you already know. if you have a straight line v versus t graph, meaning that you have constant acceleration, because acceleration is the slope of this graph, and you know that very well by now, then the average velocity occurs at the midpoint of the interval, and we've been over that. And the final velocity, if the initial velocity is 0, is going to end up being double the average velocity. And that being the case here, and that being the case when the initial velocity is 0, you can do the same thing down here. Here's your v bar, and instead of vf, we know v naught if vf is 0. Okay, and we've seen this reasoning. Okay, so knowing v bar and vf, we can find v naught in this case, just by reference to this graph, and also pretty much by reference to common sense. Okay, now we know these quantities, all these quantities down to here. What can we do? Well, we can put v naught with vf to get delta v. So those two pair up. We can't put v naught together with delta t. That doesn't tell us anything because we don't know how the velocity is changing. If all we know is v naught and delta t, we don't have that information. And delta s doesn't help. Vf will help once we get this, but so there's nothing else up here that we can pair v naught with to get new information. But if we pair v naught with vf, we do get delta v. And now, having delta v, we can pair that up with delta t to get the acceleration. And now we've got a means of determining all of these quantities. And of course, we want you to do that. I want you to do that. I ask you to do that with the data that you obtain. Now, ultimately, with that data, you're going to use a spreadsheet or something. If you've got a lot of data, a lot of lines to do a calculation on, and the calculation is always pretty much the same, it's real easy to set up a spreadsheet to do that. Okay, we did get one response after I'd made a couple of mistakes. Somebody else decided to imitate me and made one by saying that acceleration was average velocity over delta t. Now, that's not so. And if you think about it, you'll see that there are a lot of reasons why it isn't so. It's acceleration's delta v over delta t. Delta v is not even related that much to vf. You can average 60 miles an hour by going steadily from 30 up to 90. You can average 60 miles an hour by just staying at 60 miles an hour. You have a much different delta v in one case than you do in the other. Okay? However, if you're doing the thing that we really don't want you to do, okay, and that is grabbing formulas because they seem like they might work, it's real easy to grab that one because it looks so much and feels so much like this one. Okay, if you go back to the definition, what's the definition of average acceleration? Average rate of change of velocity with respect to clock time, and that's change in velocity divided by change in clock time. So this formula comes right out, and this isn't really a formula, it's a definition, and you're not going to get this one. And I have to say, you know, I'm as prone as anybody to pulling out the wrong formula, and if I'm not very careful, I can make some pretty egregious mistakes. For example, drawing this graph when I meant to draw this one. Okay. I'm going to add something here. We have, well, we can determine the acceleration of the car as it goes up this incline. We've gotten data to determine the acceleration as it comes down. What about going up? Let's try it. Ready? 1, 2, 3. Okay. Of course, you can also get it coming back down if you want, but try it again. Ready? 1, 2, 3. And let's try one more. 1, 2, 3. I wanted it to go further than that. Let's try again. 1, 2, 3. Yeah, I'm afraid to hit it much harder. I just don't think it'll stay on the track. I think it'll start rotating. Okay, just a short little clip there to go with the ones we had previously.